All right, things are really starting to heat up as we're moving into chapter 9, talking about heat notes. This is Mr. McMurray. And let's talk a little bit about heat. In the past, ancient history really, back in the 1600s, early 1700s, a lot of heat and temperature was not really understood. For a long time, they believed that most substances that would burn had something called phlogiston in them. And if they had phlogiston in them, then they would burn. If they didn't have phlogiston in them, they would not. Once it was burned, it went into the air. Plants took up the air, and that's how come plant material, if dried at least, would burn, because it had the phlogiston that had got it into the air. And of course, things that ate the plants would get the phlogiston into them. And so they believe there was a substance that caused a heat like this. And in some ideas, they're kind of on the right thing there, in that a lot of burning reactions, when things burn, require oxygen, which is a gas in the air and is taken up by plants and so forth. But they really had the wrong idea, that they thought it was a separate substance that allowed things to burn or not. But for a long time, that was an idea. Another idea later, that heat was something called caloric. Okay, caloric has to do with heat. The word we use today, calorie, comes from the same root word. Okay, and this was heat. If something had caloric in it, then it was hot. If it didn't have caloric in it, then it was cold. Things that sat out in the sun and got hit by the sun would gain caloric. Okay, and there was a substance building up in it. Okay, and that's kind of what ideas they had for a long time. Now, the first of what we think of as heat, the study of heat as we know it now, probably started with Count Rumford. Okay, Count Rumford was a military man, and basically he saw cannons being drilled out, and they would have a big piece of metal, and they'd be drilling a hole in the middle. They would be grinding. It had a blade thing that would turn and scrape off the metal, and eventually would make the bore or the hole in the middle of the cannon. And every so often they had to stop. Why? Because it generated so much heat. And so as he saw the cannon, he realized that maybe the kinetic energy, or the motion of the drill that was drilling out the cannon, created heat. So that heat was actually related to kinetic energy. And that was a big breakthrough. He came up with what we now call the kinetic theory of matter. All right. Theory of matter. Now, kinetic theory of matter, okay, or kinetic theory of heat, all right, basically said that all substances, basically the atoms in all substances moved, okay, and they're either molecules, if they're made of more than one atom, or their atoms would move, and based on how much they moved, that controlled its heat. And so heat was really tied into the kinetic energy of the molecules and atoms that make things up. And so if you were a solid, for example, the atoms were crammed closely together. All right, so if these were the atoms in a solid, they couldn't move around, because solids don't move around and change shape and do that kind of stuff like liquids and gas or fluids do. And so the atoms were so close together, all they could do is just kind of vibrate in place. Okay, if they got hotter, though, they would move faster and faster and faster, and they would vibrate faster and faster and faster. So basically, in solids, heat would cause them to vibrate faster. Eventually, if they could move fast enough, they would break loose and begin to slide around each other. Okay, they couldn't leave, they had to stay, and that would be a liquid, basically. In a liquid, you have atoms that can move around. Okay, now they have moved out, and they can move around. Say this is the container of the liquid. Not a very good bottom there. All right, they could move around inside the liquid, okay? And the more you heated them, the faster they would move around. All right, and as you heated things, if you dropped a piece of dye or food coloring in it, you could see that as it got hotter, this would move around, the dye would move around and spread out faster because of the action of the molecules hitting it and knocking it around in there. All right, now eventually, if you hit these molecules fast enough, or atoms, they would break loose into air. And so in the air, you would have these atoms bouncing around, constantly movement. Air is almost constantly moving. And so, and they would be much more spread out. So the density is getting less and less and as they're moving faster and faster. All right, and that's basically where the kinetic theory of heat or of matter came from. All right, and that's basically what we agree on today. Really, when we're measuring the temperature of something or the heat of something, how much heat it has, we're basically measuring how fast its particles are moving. Now, there is one other phase which we have not mentioned here, and that is plasma. All right, plasma is very rare on the Earth. Okay, it is not found in nature very often. Okay, relatively rare. In plasma, the electrons have all been ripped off of the atoms, which causes the atoms to have a positive charge, and the electrons, of course, have a negative charge. Now, the whole plasma as a whole would have a neutral charge because there's still the same number of protons and electrons, but since the electrons have been ripped off and they're all kind of all flowing together like in a big flow of electrons, and you just have the little proton electron nucleuses which have a positive charge, okay, and then you've got the little tiny electrons flowing all around, all right, but they're not sticking with the atom that they belong to. This is a plasma. It can be caused by electromagnetic fields, or and vice versa, it can cause electromagnetic fields, for example, like in a plasma TV or something like that. It can also be done under low pressure, like in a fluorescent light bulb. Involves plasma inside the fluorescent light bulb that gives off the light. So that can also be a plasma. It's very low pressure, though. It's sealed, the vacuum in there. And last, the most common you hear about very high temperatures, which would be, for example, inside a lightning strike and inside the sun and stars. So it's believed that plasma is very common on a universe scale because of all the stars and so forth that we can be full of it. But generally on Earth, it's fairly rare unless it's man-made, like in a plasma TV or so forth. You've seen little plasma balls where you put your fingers out and it fits a little thin filament or streak of like lightning, basically. And it has with a plasma, but it's a plasma because it's inside that ball, which is a very low vacuum, low pressure. So it's either low pressure, electromagnetic, which would be like electric on a TV, plasma TV. The electromagnetic fields are causing it, and or very high temperature, which once again obviously doesn't usually occur on Earth very often. All right, now when we talk about thermal energy, the amount of thermal energy in an object. Now notice we're talking about energy, that's not necessarily quite the same thing as temperature, which we'll talk about in a minute. But the thermal energy is always going to be equal to thermal energy is going to be equal to the potential energy plus the kinetic energy of the molecules or atoms that something is made out of. All right, and so thermal energy is always going to be equal to the potential energy plus kinetic energy. Now, if you think about it, when you heat, say, a liquid up and it changes into a gas, it has more potential, just like if something's higher up in the air, it has more potential to fall. Well, atoms have more potential to move if they are farther apart. And so the potential energy increases as they move farther. Okay. Also, we said as you heat things up, they tend to move faster. So that it would increase their kinetic energy. So we'll go from a liquid to a gas. One, the atoms are moving faster, which gives more kinetic energy, and they're moving farther apart, so they're also gaining potential energy, and therefore a gas would have more thermal energy than a liquid. All right. Now, that's thermal energy. Now, thermal energy is not quite the same as temperature. Okay, if we take the temperature of water, we take a thermometer. I'm going to borrow one from up here, ignore the scale on it for right now, but let's take this thermometer in the water. What is it actually measuring about the water? Well, the particles are hitting it, and technically what we're measuring is the average kinetic energy of the water. And we say average because is every atom in the water moving exactly the same speed? No. Some of them are hitting, they're bouncing off, there's collisions, and some energy from one is being transferred to another. And so they're all moving at slightly different speeds, but the thermometer will read the average kinetic energy because as they hit the thermometer, they will transfer some heat into there, which will make the mercury expand and go up the thermometer. So basically, uh, until the thermometer is at the bulb with the thermometer is at the same temperature and has the same kinetic energy as the molecules around it. They will transfer their heat into that until it's the same, and then it will go up and expand because it's getting bigger. Things expand when they get hotter, with the exception of ice. But everything else expands when it gets hotter, and so it takes up more space, spreads farther out, and so it will go up the little thin tube up in the thermometer, and that will measure the temperature. Right? So temperature, we need to know, is the average kinetic energy of the molecules in the substance. Right? It is the average. Some of the molecules may go a little faster, a little slower, or whatever, but on the average, that's what we're going to end up measuring with the thermometer. Now, originally there's been different scales on the thermometer. All right, take our thermometer here, and let's enlarge it a little bit so we can see it. All right, the first, actually about the same time, fairly similar, were the two that we're most familiar with, and those are Fahrenheit and degrees Celsius. Okay, Fahrenheit was developed in Germany by scientists named Fahrenheit. Okay, named in his honor, about 1730s. All right, and in order to make a thermometer, it needed to be something that people in one place could know and make a thermometer that would have the same temperatures marked, the same numbers as any other thermometer. So in order to do that, you had to have something as a standard. What is going to be 0 degrees? What's going to be, say, 100 degrees or some other temperature? So you had to have some kind of known temperature that anybody anywhere can make a thermometer and mark that, oh, when it's this temperature, that's 0. When it's 100, it's this, and mark those on the thermometer. Now, someone said, well, how could they do that back then? They didn't have the machinery that could make standardized thermometers. So that was a good question. Fahrenheit said, let's take two temperatures easily found, and they said, let's take the coldest temperature that we can make. All right, and the coldest temperature we could make for that time was if we put salt water in ice. Okay, basically, if you've ever made homemade ice cream, that's basically what you would do. You put ice cream in the middle canister, and you start turning it, and you put ice around it and put salt on it. So you end up with, as some of that water melts, you end up with salt water and ice all mixed together. Salty, icy brine. That's below the freezing point of water, which turns out to be 32. So this would be the coldest temperature. So, well, anybody could make that temperature. You just get salt water and ice and brine, make a brine out of it, which is basically salt water, mix, and that would be 0. When they put the thermometer there, mark that on their thermometer, and that would be 0. Okay. Now the other one, they said, let's make one at 100. Someone said, but boiling is 212. Well, they didn't go with boiling. They went with a very common temperature that knew everybody would know what it was, and that was 100 degrees, which was human body temperature. Okay, they said, well, that's our human body temperature. Anyone could stick this thermometer in their mouth, it would go up to this point, and they could mark that off as 100. Then based on that, they could double it up here and put 200, and they could fill in the markings in between. Halfway between would be 50, and then and so forth. And they could continue to make the markings for all the other temperatures and make their thermometer once they had these two markings. Okay, so, but human body temperature is not 100. Well, actually, when they first set this up, it was, but then later, as people refined it and got it more accurate, they realized that there were some mistakes, and so when they corrected for that, that's why we now have a human body temperature of 98.6. Not that our body temperature has changed, still the same as back then, but the scale has changed, and so they had to move it a little bit. But originally, the idea was 0 is the coldest temperature, icy salt water, and 100 was human body temperature. All right. About 10 years later, 1740, another scale was being set up. Okay, and it also wanted to go from 0 to 100. But since most things are made out of water, they used characteristics that had to do with water. So at 0 degrees is the freezing point of water. They said where water freezes, okay, when water freezes, then that's 0 degrees. So if you put it in water that's freezing and turn it to ice and mark it, that's going to be 0 degrees. And for the rest of this exciting part, we will have to wait until the next lecture, part 2. Thank you, and we'll see you there.